today's problem for our warm-up. I hope you've had fun with it. We have 3 points, P, Q, and R. So P is at 316, Q at 878, R at 276. So these are 3 points in space. And we're told that the triangle, which has these 3 corners, has area 19. Theta is the angle of the triangle at corner P. Tangent theta is what? Do we have an answer? What? E is correct. Now, where did that come from? Well, they probably gave you information because it was useful. So what do we know about areas of triangles? Areas of triangles come from cross products. And in particular, half of the magnitude of the cross product is the area of the triangle. So we say, oh, so that says that if we write down how you find the magnitude of a cross product, it's magnitude of PQ times magnitude of PR times sine of theta equals 38. Like, sine of theta is not tangent theta. We're missing cosine theta. Well, dot product gives cosine. So in particular, if I wanted to magnitude of PQ times magnitude of PR times cosine theta, it's the dot product. So we can take the dot product. Turns out that's 31. So now you take the ratio. And notice that the magnitudes cancel, so you're left with 38 over 31. There we go. Nice. Nice. Okay, well, a fun warm-up problem. So, for today. So we're going to spend the next few lectures talking about sort of solving problems. And Polya, his full name was George Polya, wrote a book called How to Solve It. And he said, look, there's really 4 main steps to solving math problems. And step 1, you need to understand your problem. And what do I mean by that? Well, do you understand what information you've been given? Do you understand what you're trying to find? Do you understand the terms? In other words, do you understand what's been put in front of you? And often, when we grade exams, sooner or later, inevitably, we get to a student and we gather around and we start saying, what were they thinking? And it reminds me, I had a favorite comic, and I couldn't find it, so I tried my best to reproduce it. It was of somebody giving a presentation in front of a big room, and like in a room like this. And the people are looking at them, thinking to themselves, what are they doing? What are they doing? What are they doing? And the person giving the presentation, what am I doing? And I sometimes feel that's what happens when people are doing math problems. It's like, I feel like I have to do something, so I'll just do something random. Well, no, that doesn't help. You should understand what the problem asks and then do something that's useful and relevant. Because after all, we want to get all the points. All right, so when you want to solve a problem, make sure you understand it. Now you might say, well, how do you understand problems? Well, you look at lots of problems. And the more problems that you look at, you start to pick up on things. And we'll talk more about that in our step 2. So there's a reason we say do problems. Do lots of problems. That's a very useful thing to do. Okay, well, today we're going to be talking about flat things. And of course, calculus loves flat things. So we'll start by talking about lines. And lines are pretty good. I mean, we've talked about lines in 2 dimensions, so we have a good handle on them. We say, okay, lines in 2 dimensions, we needed a point and a slope. Now, in higher dimensions, we don't use the word slope. But we say, well, what does slope tell us? It's telling us how we change, how we move, if you will. So we say, okay, that sounds like a vector. So like, great, that's what we'll do now. So if I'm making a line, I have a list, and it's a very short list. Very short list. I need 2 pieces of information. I need a point, and I need a direction vector. And that direction vector is pointing along the direction of that line. As long as I have those 2 pieces of information, I can find the line. Now, why do we need both? Well, I need the point to figure out where to sort of nail down that line in space, and I need the direction vector to say, where do I move? So here is sort of a way to think about it. We have here our space, and we have a line marked in green. So there's an initial point, x0, y0, z0. There's a direction vector, a, b, c. And I say, okay, suppose I want to describe points on this line. So, all right, here's another point, x, y, z. Now, what's our great sort of aha that connects all these ideas? Well, it's to say the following. It's like, well, suppose I now connect a line on my, a point on my line with the initial point on my line. That's a vector. How does this vector from the point x0, y0, z0 to x, y, z relate to the direction vector a, b, c? What's true? I mean, the picture hopefully is very suggestive. They're parallel. When are two vectors parallel? Well, that's not, that would be orthogonal. Parallel means you're pointing same direction. Orthogonal means you're pointing perpendicular directions. So parallel, what's an easy way to tell if two vectors are parallel? Well, the angle is 0 or 180. Okay. Cross product is 0. You think that cross product is easy. I like that spirit. Yes. Well, but probably the easiest way to tell if two vectors are parallel is to ask, are they the same direction? Which means, do they just differ by magnitude? And another way to say that is two vectors are parallel if they are scalar multiples of each other. Which means that if I look at the vector between these 2 points, it's a scalar multiple. That's where the t comes from of a, b, c. Now, the nice thing is you can pull vectors apart and rearrange it. So you say, every point on my line satisfies a nice relationship. Namely, I can say x, y, z, this is a point on my line. It's an arbitrary point. Well, I start at my initial point, and then I move in the direction of the line. So you'll see that ABC, that's the direction of the line, and I'm moving in it some amount. So t says how far to move along the line. So that's every point on the line. Now, oftentimes, we're going to take this is what we'd call vector form. We call it vector form because it's of vectors. And then we say, well, you know, vectors have their individual slots, their entries, and we can separate. We say, well, let's look at the first slot. X should equal x0 plus at. The second slot, y, should be y0 plus bt. The third slot, z, should be z0 plus ct. So in other words, if you pull it apart, then you get what we have here, this x equals x naught plus at, y equals y naught plus bt, z equals z naught plus ct. So this right here is what we call parametric form. So it writes the line as a parametric equation, and then this part over here is what we call vector form. Now, the nice thing is if you understand where things come from, you can read off information about a line. So, for instance, x0, y0, z0, what is that? Yeah, it's our initial point. What about your a, b, c? Yeah, well, it's our direction vector, which is acting like our slope. But now we're moving into vectors. So you can read off information. You say, if I see in parametric form, I can read off the direction vector of the line. Or vice versa. Now, there is, of course, a subtlety. And we should make a comment here. And maybe I'll put it as a warning. Warning. Lines can be written in different ways. Well, that's a very vague warning. But what I mean when I say lines, the same line can have different representations in this formula. Why do you think that's possible? Well, how could one line have different ways to be presented? And when I say different ways, just staying in parametric form. I could have one line have 1,000 different ways to be written in parametric form. Why is that possible?
Because of the starting, you can choose a different starting point?
Yeah, we could choose different starting points. If you choose a different starting point, I say, well, I don't like this point. I want to start over here. That's fine. It's the same line, but it's a slightly different expression. Is there anything else you can do? Yes?
Go in the opposite direction?
Okay, yeah, you can change ABC a bit. What can you do to your direction vector? You can scale it. And so it's also possible to scale your direction vector. So just be careful. With lines, it's very possible for two people to get the exact same line, but they look at their instruments and say, these look different. No, they're not different. They're the same. All right. Well, what should we make a comment about? Well, I think when it comes to making lines, the hard part is usually not the point. Not usually. In one or two cases it is. Your main energy here is going to be the direction vector. And so how do you find your direction? There's a couple of things. If you have 2 points, that's enough to make a line. So, okay, let's test this theory out. So find the line connecting. I claim this will work. Can I get 1 point?
1, 2.
How about a three-dimensional point?
4, 5, 7.
All right. Someone said 3, 2, 1. And someone else said 4, 5, 7. Give the answer in parametric form. So intuitively we say, oh yeah, 2 points, that should make a line. And so great. So we have to think about how. So how can we get a direction vector between 2 points? What do you do?
Make a vector?
Yeah, you should make a vector, right? I need a vector. I should make a vector. What do I use to make my vector?
The 2 points.
The 2 points. Say, hey, I have 2 points. I just have to figure out the vector that connects those 2 points. What's a vector that connects our 2 points? Well, it doesn't matter which one we call the start and the finish, so let's suppose we call this one the start. Going from 3, 2, 1 to 4, 5, 7, how much do we change? 1 in the x, 3 in the y, and 6 in the z. 1, 3, 6. Okay, now is that our line? No. But they told us in parametric form, so we say, great, that makes it easy. So we write down our x equals y equals z equals, and then we say, okay, we're going to have sort of 2 places we have to fill numbers in. And we just remember what goes in to where. All right, what goes into our first column? A starting point. Now, which one do we use? It doesn't matter. It'll be the same line, even if they have slightly different expressions. So, first one sounds like a reasonable thing to do. What goes in this column? Yeah, what we just found, 1, 3, 6. And there we go. We're done. We found the line. X equals 3 plus t, y equals 2 plus 3t, z equals 1 plus 6t. Life is good. All right, so 2 points, all right, we can get a direction. But I will say that something else that frequently happens is you say, well, it's possible that you might need to do a cross product. Now, if you're going to do a cross product to find a direction, what do you have to find?
vectors.
You have to find vectors, but more importantly, what's true about those vectors? We need two vectors, which are, oh good, perpendicular to what?
Each other.
Well, not to each other, but perpendicular to what we want. We want the direction vector, so we just say, are there two vectors, both of which individually are perpendicular to what we want? Now, the vectors themselves don't have to be perpendicular to each other, but they do have to be perpendicular to what we want. And if we can do that, we'll find our direction vectors. By the way, this is one of the reasons why they love asking questions about lines and planes. There's two key aspects. One, can you get your geometrical aha? Do you understand the geometry? And two, can you do cross products? Because cross products show up a lot. Word of warning, word of warning. Okay, so that's a little bit about lines. Suppose we have the following. We're given a line. So here's our line. And in case you're wondering, wait, is that our line? I'll just mark this as our line. So now there's no mistaking it. That's our line. And we're given a point not on our line. And we're asked, how far is this point to our line? Find the distance from P to our line. Well, I've sort of given a big hint of what to do. We can find a point on our line. So here's Q. It's a point on our line. I'm not claiming that it's the ideal point. The ideal point would be the one that's closest. That's a little bit harder to find right away, but just pick any point. And then you can say, well, if I have 2 points, very easy to find the vector between those 2 points. And if we have our line, we also have the direction vector of our line. So we can talk about the angle between them. And this is sort of the great, if I think about this as a right triangle, I can get a pretty good handle on the hypotenuse, and I want the opposite side. That's a sine thing. So sine relates opposite to hypotenuse. So I say, okay, so the distance is the magnitude of the hypotenuse times sine theta. And when you see sine theta showing up, you're like, cross product. You say, well, okay. Well, where does theta between? Theta is the angle between QP and V. So you say, well, wouldn't you know that this is the same as the magnitude of QP, the magnitude of V, sine theta, over the magnitude of V. And then the upstairs becomes the magnitude of the cross product. The direction between an arbitrary point on your line and the point you're trying to find the distance to with your vector V, divide by magnitude of V. So that's a formula. Now, I don't memorize this one. I have other ways of dealing with this, but I tend to rely more on geometrical intuition. So it turns out that geometrical intuition will get you very far. And we'll talk about more as we get into planes. Yes, I think that's all I want to say about that part. Any questions about lines? Okay, let's move to planes. So if you think about what a line is, it's sort of a nice, you'd think about it as a one-dimensional flat thing. Planes would be like a two-dimensional flat things. It's like a piece of paper. That's what a plane is. And so now we're thinking about, okay, what do planes have? Well, what do you need to make a plane? And someone said slope. Kind of. You definitely need a point, because you have to locate your plane somewhere in space. So point, that's true. Now, the problem with the planes is, how do you handle direction? Because if I am a plane, and I'm, say, here's my point, And I say, well, which direction does the plane go in? Well, the answer is it goes in many directions. I can go in lots of ways, depending upon which way I head out on my plane. So the plane itself contains lots and lots and lots of directions. Okay, that's bad. So we want one direction. So what do we do? Well, the answer is we take advantage of the fact that we're in three-dimensional space. And then it's like, well, plane is a two-dimensional. I have one dimension left over. So let's take our important vector and we'll call it this direction. So this is perpendicular to the plane. And in particular, when we talk about the vector, we have what's called the normal vector. So whenever you hear the word normal, you should think perpendicular. So the normal vector is perpendicular to every vector in the plane. And this vector, it's a very good vector. It deserves a star. Very, very useful vector. And again, when we say every vector, no matter which vector you pick, it's always perpendicular. So all these different directions we could go inside the plane, we're guaranteed to be perpendicular to it. Okay. Well, how do we translate that and use that to find a formula? So here's a plane. My x naught, y naught, z naught, that's a point on my plane. And then I put my normal vector coming out. That's perpendicular to my plane, and it has entries A, B, C. And now, x, y, z is an arbitrary point in the plane. What to do? Well, let's connect. I claim we can find that vector. It's a vector between 2 points. So you just subtract x minus x naught, y minus y naught, z minus z naught. What's true about this vector? It's perpendicular to the normal vector. Why is this vector perpendicular to the normal vector? Yeah, the normal vector is perpendicular to everything in this plane. And this vector is connecting two things in the plane. And so it must be perpendicular. Well, if two things are perpendicular, what's true? Dot product has to be 0. So we get that A, B, C dot x minus x naught, y minus y naught, z minus z naught equals 0. And this is because it's perpendicular. All right. Well, we're almost home free. So this becomes A times x minus x naught plus b times y minus y naught plus c times z minus z naught equals 0. If you expand and rearrange, you get a times x plus b times y plus c times z. So you get your ax, by, cz. And then you can move the other terms to the other side. That's a times x0 plus b times y0 plus c times z0. Now this piece of information, that a times x0 plus b times y0 plus c times z0, is fixed. It doesn't change. You move this point around, x, y, z, that doesn't change. So we just give it a name. ax plus by plus cz equals some number d. So every plane in three-dimensional space has that form. ax plus by plus cz equals a constant. All right. So let's try something. We'll do a question. What is the normal vector for the plane and 2x minus 5z equals 3y plus x plus 11. Is that possible to find it? Now, there's a misleading word here, but that's okay. We'll fix that in a minute. Can we find this normal vector? Ah, I see a hand raised.
Could you set it back to the equation that you just stood above, and then manipulate it back to a function of like setting it equal to 0, and then like can you reverse the process?
So someone's saying, hey, why don't, you got this handy equation right here. Why don't you make it look like that? This is a wonderful idea. It's like reducing to a problem that we've already solved, right? So let's make this look like that. Okay, so what should we do? Let's put all our variables on one side, the number on the other side. How many x's do we have? 1, right? 2x. How about y's? Minus 3y. How about z's? Negative 5z equals 11. Now, oh, sorry. That's just a very poorly written 1. See, there you go. See, now it looks like a 1 times x. All right, x minus 3y minus 5z equals 11. Thank you. Now, I claim we can almost stop, or at least at the very least, we can write down the answer without doing any more work. We subtract x. So there's an equal sign here. It's not a plus sign. All right. What's the answer we write down? And how do we get it?
Just flip the signs, so that way you get your 2 plus signs in the middle. So we'll just do like negative 11 equals negative x plus 3y plus 5z.
What?
Never mind.
You're doing advanced math here. Notice our normal vector, A, B, C, yes? Notice here, A, B, C. So what am I looking for? Your coefficients. So, what are my coefficients? 1, negative 3, negative 5. And we're done. So if you have an equation for the plane, you can read off the normal vector once you put it into the right form. So it's good to know. It's like, oh, now you might say, well, wait a second, what is this 11 doing? That's a good question. What is the effect of this 11, essentially, if we think about what's happening? If I change this 11, what am I doing to my plane? Yeah, I'm shifting it. Do I tilt it in any way? No. So this is purely, you can think of it as a shifting factor. And I will say we are heavily biased towards direction. Heavily biased towards direction. So you will see that most of our work is going to be in the normal vector. In fact, I'd say the vast majority of our work is going to be in finding the normal vector. And how do we find the normal vector? What's our go-to tool?
Cross product.
Cross product. Now, dot products are great for checking if things are perpendicular, but if you want to make something perpendicular, you want to pull a cross product in, because the inherent thing about a normal vector is that it's perpendicular to everything in the plane. You're like, oh yeah, cross product. All right. So, any questions?
I don't understand why the 11 shifts the plane.
Sure. Okay. So, but let's think about it in a couple different ways, and I'll try to argue 2 ways, and then you can say I don't like either one. But the first thing is that if you change this 11 you don't change your coefficients, so you don't change your normal vector. So that says you have the same normal vector. So if I'm on my normal vector, the only thing my plane can do is go slide along that normal vector if I change that parameter. So the only thing that can happen to the plane is moving perpendicular to my normal vector. So that's one way to think about it. Another way to think about it is, where did this 11 come from? It's actually this sort of a dot product of your normal vector with your point in space. So by changing this dot product, you had to either change your normal vector, but you haven't changed your normal vector, or you had to change your point in space that you're anchoring. So your anchoring point has moved. So that says, oh, I've been moving my plane, but I'm still parallel to what I started with. Either of those explanations seem reasonable? Okay, I like the first one too. All right, other questions? Good. Suppose we want to find a plane. Well, let's try this out. So, how many points do you need to make a line? 2 points. How many points do you need to make a plane? 3 points. Okay. So find the plane containing the following points. Okay. And let's be nice to ourselves. Give ourselves reasonable numbers to work with.
3, 1, 2.
Well, someone has suggested 3, 1, 2. 1, 1, 1. Okay, we're very nice to ourselves. That's all right. And we need a third point. 4, 6, 8. Who do we appreciate? All right. Huh. I got something slightly different. I'm not saying I got it right. Did we get any other answers?
5x plus 11 y minus 10z equals 6.
Huh. That's what I got. 5x plus 11y minus 10z equals 6. All right. Now, what's our thought process? We have points. We have lots of points. So if we need a plane, what do we need? We need the normal vector. So it's like, okay, if I want a normal vector, put 2 vectors in the plane and take their cross product. So form 2 vectors in the plane. Take their cross product, and you get out a vector. I do a quick check to make sure it's perpendicular, because I'm always paranoid I make mistakes, because I do make mistakes. These are our coefficients. So it's like, okay, we almost have our plane except for this number. How do you find the number? Plug in a point. But which point? Which one will give us the right answer? All of them will. So which one do we pick? The easy one. Remember, we love ourselves. So we always do things the easiest way we can. So we pick the easiest point and we clean it up. All right. Now, there's a tip here. Normal vectors are not unique. And so when we say the normal vector, that's actually misleading. It's a normal vector because you can scale. So if you do your cross product and everything has a factor of, say, 6, just pull out the 6 and work with what's left. Make things easy on yourself. Why should we make things hard on ourselves? All right, so that's the idea. Our game plan almost always is find 2 vectors which are going to be perpendicular to our normal and take their cross product. All right. A few more things that we have to mention. There's a formula for the distance to a plane. And let's suppose that this plane has the formula ax plus by plus cz equals d. And this point, we'll call it x1, y1, z1. And I want to say, what is the distance to the plane? Well, We have the normal vector because we can read off the coefficients. And it's like, well, it'd be great if we had that point, but maybe we don't have that point. So what can we do instead? Well, let's just pick a point in the plane. It's usually not hard to find a point in the plane. And so that says I can find a vector. This vector, QP. And now we say, well, what do you know? It's a right triangle. And I have the hypotenuse. I want to know something about the adjacent side. And this angle is actually the angle between these two vectors. Now you might say, what? But remember, vectors can be moved. So I can move the normal vector up, and I can move QP, slide it along, and you'll see that, lo and behold, it's like, oh yeah, it is. These vectors, this angle theta really is the angle. Well, so the distance is the magnitude QP times cosine theta. Cosine, that's a dot product. So you say, you're right, it is a dot product. So we say, okay, imagine if we did the following. We took, let's say, the magnitude of the normal vector times QP cosine theta over the magnitude of the normal vector. Well, that's n dot QP. Now, I should say this is technically not right, so I'm going to fix that. Does anybody know what the issue is with this saying magnitude of QP cosine theta? No? The problem is it could be negative. So you should throw an absolute value there. So take the absolute value of n dot QP. All right. Which one do you want to handle first, the upstairs or the downstairs?
Whatever you want.
Whatever you want. Oh, you guys are the first ones to ever say that. You're the best. You're the best. All right. Okay, we'll do the upstairs. Okay. So the normal vector, that's your A, B, C. And I should give Q, I'll call it x naught, y naught, z naught. It's a point in the plane. So this vector is x1 minus x naught, y1 minus y naught, z1 minus z naught over the magnitude of n. Now, magnitude of n, you can just read it off because you know what n looks like. It's, oh, I didn't write it down. It's ABC. So that's the square root of a squared plus b squared plus c squared. Okay. And like, okay, great. But does anything happen? Well, yes. I'm going to multiply, and I'm going to regret doing all this in front of a live studio audience. But just multiply the top out, because that's what a dot product does. And then after I do that, I'm going to rearrange things. So this becomes ax1 plus by1 plus cz1 subtract ax naught plus by naught plus cz naught. And the punchline is almost here because I'm running out of space, so I can't, it has to come in the next line. I claim that something nice happens. You have ax1 plus by1 plus cz1 minus something over the square root of a squared plus b squared plus c squared. Something very small that can fit in that much space. It is D. Why is it D? Because of our formula. Every point in the plane, and that's a point in our plane. So ax naught plus by naught plus cz naught equals D. Now, I don't memorize this. I can derive it, but there are other ways to figure things out. So, for instance, it says, hey, I can tell you the distance to the plane, but you say, well, I don't want the distance to the plane. I want that nearest point. I want this point right here. And the formula will say, best I can do is distance. So is there a way that we could use our geometrical intuition to get that point? So suppose I have a point P, and I want to find this point, R, which is the closest point. What can I do? What's true about this line? It's perpendicular. Do I know the direction arrow for this line? Yeah. The normal vector, which is normal to the plane, also is the direction vector of this line. I have a point and a direction. I can make the line. I have a line and a plane. What can I do? I can check to see when they intersect. So you can find when a line and a plane intersect, and then you have your point R. So a lot of basic things come down to saying, hey, what can you do with the geometry? All right, so we're almost done with time. Quick cool down problem. What is the formula for the plane which is tangent to the sphere, x minus 4 quantity squared, plus y plus 3 quantity squared, plus z minus 1 quantity squared equals 29 at the point 614? So we have a bunch of possibilities. 2x plus 4y plus 3z equals -1. 2x plus 4y plus 3z equals 28. 4x minus 3y plus z equals 15. 4x minus 3y plus z equals 25. 4x minus 3y plus z equals 29. Put on your geometrical hats. Think about the geometry of the problem. That's almost always how you solve these things. Think about the geometry of the problem. Your geometrical intuition will make or break you in this class. It will decide whether you're somebody who's going to get that A or someone who's going to get that A minus. No. It's oftentimes A minus versus a B plus. And I know you've only had a few seconds to look at it. Is there anyone who has brave enough to throw out a guess? B. B is the correct point. In fact, you can rule out A pretty quickly because 614 is not a point on that plane. And then you say, well, what's our geometrical aha? The vector, the normal vector, is from the center to where the point of tangency is. So that makes the normal vector quick to find, and then you can find the rest of it. All right, that's it for today.